Adam is a student in my group. He started out with the quest to make a new kind of sensing device, optical sensing device, specifically endoscope-like probes, where we wanted to do discrete imaging. We wanted to waveguide bundles that delivered information from one place to another in pixelated systems. I think what he's talking about today is the eventual fabrication system he came up with to do that. And this has got a lot of interest, so one of the things he's heading off to the Max Planck Institute to go study neurons, because there's lots of fun things we've got to do with the technologies. Thanks, Bob.
As Bob mentioned, this is my thesis research. The title of my talk today is called Liquid Deposition Photolithography for Three-Dimensional Polymer Structuring. So why do we want to do three-dimensional structuring? There's actually a lot of different applications, from optics all the way to biophotonics. So in the bottom right here is an image of a tissue sample. And its major purpose is to provide a physical modulus for cells to grow together and to grow a new tissue. On the left here is an image of a negative index of refraction material, which gives you, again, a property that you can't find in nature. And on the top right is an image of a photonic crystal, which gives you some sort of superior optical property. So the applications do range from photonic devices all the way to biophotonics. So this is the outline for my talk. I'll begin by talking about the way this is currently done and show that there is a hole in some current techniques. I'll then go and talk about the thing that I've been developing for the past 3 or 4 years called liquid deposition photolithography, LDP for short. I'll then get into some example fabrications I've already created, and then, assuming there's time at the end, I'm going to talk about applying for the international rotation for the COSI program. So before I jump in, I'm going to ask each three-dimensional structuring technique if it meets these 5 requirements. So firstly, I wanted to be able to structure both physical and index structures, meaning binary materials that are not there, and index being a change in its refractive index. I want it to be high throughput, meaning I can write the structures fast. I want it to be able to do arbitrary structuring, meaning I don't want it to be limited by to just periodic structures, for example. Fourthly, I want it to have high resolution in all 3 dimensions, sub-micron resolution. And finally, I want it to be millimeter scale or greater in all 3 dimensions. And the reason I want all 5 of these things is because photonic devices, and particularly 3-dimensional structures, increasingly require greater resolution to get these superior properties. However, if you want to do anything with them, like in the device region, you need to make them large as well. So the first technique I'm going to talk about is multi-photon absorption. In this technique, you take a femtosecond laser and you focus it in a material with a high numerical objective. And since it's multi-photon absorption, you restrict autofocus exposure, localizing your event just to the focus. And so in glass, you create an index change, shown right here, or in polymer, you create a binary structure, in this case, a wood pile. However, the problem is you can't get both at the same time. You get either index or physical structures. But the big problem is this is a very low throughput technique. So for example, in this particular structure, the write rate for it was 13 meters per millimeter cubed. So you're really limited to very small structures. Okay? So how you can improve upon that is use 1 photon absorption instead of multi-photon absorption. And so, in this particular case, we're not localizing our point source anymore. And so, in order to get that localization, what they do is they write their structures in a layer-by-layer method, and then use a UV absorber or an absorber for the light, so you don't get penetration through the depth And so you're just localizing it to your single layer. However, you still only have a single scanning point that's building your part, so it's still relatively low throughput. But the biggest thing you've given up by going away from the multi-photon absorption is you're not submicron resolution anymore. You simply can't blow it up the material with enough absorber in order to get down to submicron. And so you're limited to around 20 or 30 microns in depth resolution. How you can improve upon this is by adding a formal mirror device to the system. All that is a dynamic pattern generator, and so now you're writing 2 megapixels at a time instead of a single scanning point. And so what that gets you, specifically with dense structures, is a great increase in throughput. However, you still have that nasty 20 micron resolution problem. How to get that depth resolution back? What people have done is do multi-layer mask projection lithography. So how this works is you would first spin down some sort of resist, and then you would expose that with projection lithography. Projection lithography is a really, it's a highly developed technology. You get resolutions down to 22 nanometers, as well as throughputs up to 100 terabits per second. So they got the silicon wafers flying in and out there extremely fast. However, once you finish that step, you then have to go around this loop, doing etching, spinning, etching again, spinning again, planarization, etc. And so after 10 or 15 trips around the circle, your grad students revolt and you are left with a 15-layer structure. And so the big problem with this is all of these extra processing steps. They really slow down the process, making it not a large-scale technique, especially in depth. So how you can get to fixed structures is by doing volume holography in a self-developing photopolymer, as shown right here. So in this technique, you take 2 beams, a reference beam and another beam, creating a 3-dimensional pattern of light, and exposing that material. And the real magic in this technique is in that material. It will usually contain two different monomer systems, where the first monomer system is thoroughly cured. This is setting up a physical scaffold for that second monomer, which is photopolarized by your beam of light, or your 3-dimensional pattern of light. After you expose it and polarize it, you then get mass diffusion of the unreactive monomer from the dark regions to the light. This increases the density and therefore the index of refraction, thereby copying your 3-dimensional light pattern into your storage medium. And so this is great because this exposure only takes a few seconds. However, you don't get both physical and index structures because you've thoroughly cured your sample and you can't change the physical modulus. But the biggest problem is you're very limited in your structuring potential. You can't create every 3-dimensional pattern like you want. And additionally, for transverse structures that are greater than 100 microns, the diffusion time becomes months or even years. So this is just a summary of all those different techniques. And so from this table, you can see you get a feeling for what you give up in order to get complexity. For example, as we move along this direction, we're generally increasing our resolution and complexity. However, as we do that, we're generally decreasing the throughput. As shown right here, we're going from around seconds per millimeter cubed to infinity because it's never really been done before. Another thing of note is the multi-photon or 2-photon absorption seems to be pretty good. You get great transverse and depth resolution, and you get arbitrary structures. If you just move this down a little bit, you could build lots of stuff. The problem is with that particular technique is throughput is inversely proportional to the area you expose, and so it's just physically limited by the technique that you've chosen. Okay. So now I'll talk about the technique that we've developed in our lab called LVP, and then show some modeling showing that work. So this is the conceptual layout for LDP, and you'll see a lot of the same bits that I showed in the previous techniques. So on the left here, you can see we're using a holographic photopolymer. In contrast with the volumography though, I'm not going to thermally cure one of the monomers. I'm going to leave them both initially liquid. And that's important because how I'm going to build the three-dimensional volume in my chamber here is by repetitively flowing that in and repetitively patterning it, and repetitively layering it, building my three-dimensional volume layer by layer. And so how I'm structuring each layer is through projection lithography, which again is a very fast process, as well as high, or with the potential to be very high resolution. But the key here is that since I'm using that holographic photopolymer, I'm now using a self-developing material. So all those processing steps, all that etching and planarization, I no longer have to do anymore. So I can now do conventional lithography, except do it fast. And so just like conventional lithography, my resolution will be set by my projection lithography optics. However, in contrast to conventional lithography, my depth resolution will be set by this moving platform, an injection of my liquid photopolymer versus spinning. And showing that you can indeed pattern this liquid photopolymer in this way, I have exposed the seed buffalo in between two unpatterned layers. And on the right here is a DIC image, or differential interference contrast microscope image, and it measures the derivative of the index. So the fact that this looks like a surface feature means I have an index change in the form of this buffalo in between the layers. And so I'll be showing a lot of these images. So every time you see a surface pattern like that, it's showing that I do have nice index contrasts in my image. So these are the process steps for how LDP actually works. So we start out with a chamber where we have liquid monomer inside, our platform, which is going to do our injection, and then this glass PDMS mold, which is going to allow that optical pattern access. And the reason the PDMS is there will become apparent in a second. So the first step is I'm moving the platform down. This is going to inject my new liquid monomer layer. And I'm then going to come with some optical projection in that particular layer, either through a chromite glass mask or a DMD or whatever. And the first thing that's going to do is consume oxygen within that layer. So these photopolymer materials are inhibited by oxygen, and oxygen is free to flow through them, and so oxygen acts as an inhibitor to the system. So before you can start polymerization, you have to consume the oxygen in those regions. While this is going on, we're getting the fusion of oxygen from that PDMS. What this is giving us is a thin, inhibited liquid layer sitting right next to our gelled regions, shown right there. And what this inhibited region is going to allow us to do is repetitively layer. So if we didn't have that PDMS mold there, what would happen is we wouldn't get that diffusion, and we would simply stick straight to the glass, and we couldn't repetitively layer. So we couldn't build a three-dimensional volume. But after we've gelled those areas we've exposed, we get diffusion of high index monomer into those regions. This is going to increase the index and density. We then come in with a flood cure. This is going to freeze those high index regions in place, as well as desensitize that material. We would then repeat this step one, inserting the next layer by moving the platform down, and repeating those steps to fabricate the next layer, building up our three-dimensional volumes layer by layer. So this is what it looks like on the analytical table. On the right here is our chamber with all our processing steps, and we're using a 365 nanometer IM argon laser and a rotating diffuser to create our projection system. And we're using a chromite glass mask to create our patterns, and as well as unstructured light, and switching off and on shutters in order to control what particular light it gets, depending on what step you're on. So the next question is, how do I really understand the dynamics of what's going on in the system? As I already mentioned, that PEMS mold is very important to the system. It's really the enabling technology and what makes everything go. And so we'd like to understand what's going on down there a little bit more. And so in order to do that, we developed a model where we're going to monitor the monomer, the photoinitiator, and the oxygen in the system and see how we can develop and see how our structures develop. So the first thing you write down whenever you're creating a model for these photopolymer systems is you write down the radical density as a function of time, and that involves radical creation. This is where a photoinitiator absorbs a photon of light, cleaves, and becomes a radical. The next term is bimolecular termination. It's where two radicals find each other and terminate, so you've gone from two radicals to zero, which is why there's a 2 right there. And then finally, unimolecular termination, where a radical has found an oxygen molecule and then terminated itself. And so lastly, I'm going to use the quasi-steady state approximation, which means this gets set to 0. I can use this approximation because my intensities are low and the exposure times are relatively low. And so this allows me to solve the radical density within my system, which then allows me to compute the oxygen, monomer, and polymer densities in the system as a function of time and space. And so these will have a diffusion term as well as a consumption term, where the polymer, since it can't diffuse, is really just created. And so the final thing I need is what material I'm going to use, because all of these KPs, DMs, etc. Are highly material dependent. And so I'm going to use polyethylene glycol diacrylate as my basic material. Doing this for 2 reasons. Firstly, it was the material we first started using when we were doing experiments, so it seemed natural to use that material. And secondly, this guy Doyle, who's done a lot of work with PEMS, went out and within a bunch of papers found all these constants for us, and so we could just grab those constants, put them into our model, and expect good results. And so what I'm going to look for in my model is measure these concentrations of oxygen, monomer, and polymer as I turn on the light, and monitor them until I turn off the light and see what I get. So these are the results from the simulation. As you can see, I get an inhibitor density right next to my PEMS, which is oxygen in this case. And so what happens in my system is like a bathtub where I have full inhibitor and monomer with no polymer. As soon as I turn on the lights, I in effect will pull the cork on a full bathtub, depleting all of the oxygen or water in the system. However, what the PEMS is doing is sort of like a faucet. It's turning on the water or oxygen, allowing it to flow in, but the drain is draining faster than it can keep up in the back. And so what it gives me is a 1 micron thick inhibitor region where I get no polymerization. And so what this allows me to do is allows me to build up many layers because I have this 1 micron inhibitor region, and so I can build layers in this way. But what this also gives me is it gives me a 1 micron thick liquid layer of monomer and a concentration gradient into the polymer. So what this is going to allow me to do is both allow me to diffuse axially, which we didn't have before. And it's also going to provide this 1 micron thick monomer, which will aid in rapid fabrication. So in normal systems, for example, if you expose a grating, you can only get transverse diffusion because you axially everything is the same. You have no concentration gradient axially. Where here, I do have a concentration gradient axially, and so I can diffuse large transverse structures now. And then finally, I'd like to point out that this polymer boundary right here is relatively sharp. It's around 100 nanometers or so. And so that at least tells me that I think I can build layers really, really thin. And that's important because you really care about achievable transverse resolution in the system. So assuming that layer thickness is set to my depth of field, this shows is that I decrease that layer thickness, decreasing my depth of field, I can get better resolution. And so right around 100 nanometers, I get my max resolution where my optics stop working because I don't have the achievable NA within my objective. So 100 nanometers would be a nice place to operate. So this is extending that simulation to 2 dimensions now. So now I've changed my light pattern from just doing a flood cure to now doing a grading. And so the main thing that I get from this, not only do I see this inhibitor region in 2 dimensions, which is nice, but I see a difference in dense versus sparse structures. So in this region right here, it's relatively dense. I have lots of stuff, lots of light in a small amount of space. And so what happens is shown by the oxygen, I get diffusion from the dark to the light, and I get pretty much a carbon copy of my pattern, shown by those white lines right there. However, on the sides of my exposure in this region, on those sides, I have a sea of oxygen. And so what happens is I actually get a feature shrinking at those sides. And so what that says is when I write sparse structures in particular, I'm going to get a smaller feature size than I would actually expect. And I'll actually show this later in the talk. And so the last thing I'm going to ask for my simulation is how fast I can go and what parameters should I operate at. And so what this plot is showing is the fabrication time to write a millimeter thick sample versus layer thickness. And so for each fabrication, I have both exposure time and diffusion time. And so not surprisingly, as I decrease the layer thickness, increasing the number of layers, the exposure time to write all those layers goes up. Makes sense? However, since diffusion time scales as layer thickness squared, as I decrease my layer thickness, the total diffusion time goes down. For example, if I have a certain thickness I want to diffuse, if I decrease that by a factor of 2, my diffusion time for each layer decreases by 1/4. I've doubled the number of layers, but my total diffusion time is now half what it was, which is why this is a linear downslope. Okay? However, that doesn't last forever, because if I keep decreasing my diffusion time, eventually I'm going to reach a point where my exposure time is going to dominate, meaning the exposure time is longer than the diffusion time. And for my particular material system, that point is around 1 micron, where I get optimal thickness for fabrication time. But just in general, this is pretty cool, because this tells me that as I increase my depth of resolution, I actually record faster, which is something you normally don't get in systems. So now I'm actually going to get into some example fabrications I've done, as well as a parallel optical waveguide array. And then talk about the specific material that we used in those structures. So this is the material I use, the formulation. It's a 2-component photopolymer with a UV initiator. So the first component is the matrix monomer. It's polyethylene glycol diurethane methacrylate. As you can see, it's generally a large molecule, and its index is very low. The second component, though, which we call the writing monomer, is very small, meaning it's much more mobile and easier to move, and it has a relatively high index. So in the system, we would inject both of these into our exposure region, and then expose it to some pattern of light. And so in the areas that we exposed, we've now gelled, meaning that both the writing and matrix monomer have polymerized together. We would then do diffusion of the writing monomer, the trigonal phenylacrylate, into those gel regions. We do not, however, get diffusion of that matrix monomer into that gel region because the diffusion coefficient of that matrix monomer is much, much less than of the writing monomer. This is going to get increase the density in index of that exposed region, and especially of the writing monomer, meaning we're going to get large refractive index differences between the two regions. We finally then come up with a flood cure, which is going to gel the sample and leave us with a high index region and a low index region. So this is the estimated index change for our particular material. We assume full conversion of tridromal phenylacrylate and complete replacement, which just means that in the exposed regions we assumed 8% tridromal phenylacrylate, and in the unexposed regions we assumed 4% tridromal phenylacrylate, and measure this with an aggregate refractometer and found our delta N to be 3.6 times 10 to the negative 3. And this is pretty typical of commercial grade photopolymers. Showing that we can actually design a material well, we did a control experiment where at this time, instead of patterning the buffalo, we patterned the CU seal. And on the left, we put in no trigonal phenylacrylate and found no index change within the sample. We then put in 4% trigonal phenylacrylate, and we see really nice contrast and really good fidelity of that CU seal. Showing that we can indeed stack layers. Here, we first pattern the CU buffalo, 3 microns thick, come back, and then right on top of that, we've polymerized a CU seal. And as you can see, we get really nice contrast of both. Showing that this system can indeed get sub-micron resolution, we exposed a 1 micron hologram, showing that we do indeed get sub-micron resolution, and also an light response as well. Showing that we can really program this thing up to give us any type of structure we want. Here we've exposed a single layer with a photonic crystal fiber structure. And as you can see, not only do we get nice analytic index, but we also do see a nice copy of the defect within that sample. And so showing that we can write single layers and a couple layers, but can we actually make a device of this is the next question. As Bob mentioned, when I first signed up with the group, I was first tasked to create a parallel optical waveguide array. So I figured that would be a good device to test to see if this could indeed fabricate photonic devices. So on the left here is just a DAC image of a single layer. We built 100 layers of this particular pattern, each measuring 12 microns for a total of 1.2 millimeters thick, with those particular writing parameters, with a throughput of 1.2 hours per millimeter cubed, which is obviously much faster than the 13 years. And this is the performance of that waveguide array. So here we've illuminated the sample, our one end facet with a plane wave, and imaged the other end with the camera here. And as you can see, we're getting really nice transmission throughout the entire sample. Next, we wanted to probe the modes of our waveguides and to see if it was single or multi-mode. And so what we did was we focused down a laser beam onto a single guide, trying to mode match onto one of those waveguides, had that property down the waveguide, be reflected by a mirror, reflect back, and then be imaged onto a camera. And what we found was the mode size was around 5.5 microns, which was actually kind of weird, because the pattern that I exposed it with was around 10 micron diameters, so that's sort of unexpected. You'd think you'd get 10 or 12 micron mode. Also, if you have an index change of about 3.6 times 10 to the negative 3, you would assume that your mode size would be like 14, 15 microns. So we have a tool in our lab that allows us to measure the index at the end facet of our samples we create. And so we did a scan, And we found the index change to be all the way up to 0.1. And so we're extremely confident in the results. So first of all, you can see it has the same periodicity as a regular array, which is nice. But also you see that the mode size now is 5 microns. So that makes sense. So let's see. And the reason we believe that the mode size for the wave guide was 5 microns was from the modeling I showed before. What's happening with those 10 diameter guides is we're getting diffusion of oxygen transversely, which is shutting the polymerization down up until the center, where we're now only getting a 5 micron guide instead of a 10 micron guide. But this is pretty exciting because 0.1 index change is pretty impressive. How it compares to other techniques is actually quite favorable. So in multi-photon absorption in glass, you get around 0.001. In commercial holographic photopolymers, you get 0.005. As you can see, LEP is 20 and 100 times greater than that. And so this allows greater flexibility and design in different photonic devices. So to conclude this portion of my talk, I've shown different features of LPP, 3D programmable structuring, as well as sub-micron to centimeter resolution. I've shown large part volume with fast fabrication. And since we're doing radical photopolymerization, this technique can be very flexible. And since it's starting from a liquid state, you can dream up new materials with different forms of index change other than diffusion and different crazy ideas. The problem is there's more different materials you can use than there's time to test in the lab. And so I've shown different integrated optics applications. We hope to move toward different tissue scaffold applications as well as polymer programs. And so lastly, I'm going to talk about international rotation, really how to get started and why you would want to do such a thing. So I don't know if everybody knows, but COSI gives an opportunity to do a 1 to 3 month international rotation in the country and research group you're choosing. And it also counts as one of your required 3 rotations, so another reason to do it. But the main reason is this one right here. COSI pays for your travel, housing, and meals. And so you basically going to go visit another country and research group for free. And so far, only 2 students, including myself, have done or are going to do rotations. And only Switzerland and Germany have been represented. So people need to get to work on applying for this, since there's only a year left in the program. So why would you want to do this? Obviously, why not? It seems like a great opportunity, right? But it can really get you another chance to work with a research group that you otherwise probably would never have worked for in your life. You get to develop an international collaborator, both for yourself and your advisor. You get to do something you can't at CU, which is nice. You get to complement your domain of expertise. I'm going to do neurobiology research. Obviously, I can't really do that in the group I'm in now, although we want to move that way, so it's a good way to lead into that. Also, assuming you actually want to get a job after you graduate, it's never too early to start developing contacts, even if it's in Germany or wherever. You can develop unique skills, you get to learn a different language, training for project leadership, all good things. And apparently students actually get windows in other universities, so that's really the only reason I'm doing it. We have to check you now. Yeah. So the question is, I want to go, but how? So the first thing you have to do is find a group to work with. And so there are 3 main ways you can do this. Probably the easiest way is with an advisor connection. Your advisor's buddies with somebody in Switzerland, they talk, smoke cigars, and decide you're going, and everything's good. However, there are a couple other options. You can choose to work with a COSI international partner. You can just talk to Ariel, and he'll set you up with someone that whose research you might be interested in. And then the final one is I call it cold calling, because I had no connection to this group whatsoever, and I was able to make it happen. And what I refer to by cold calling is you read lots of papers, and you find out who you want to work with. Oh man, that guy's doing really cool things. I would love to go live in Germany and do neurobiology research for 3 months, for example. And so you decide you want to go there. So then the first thing you have to do is develop some sort of connection with that person or with that research group. So either by emailing, calling, carrier pigeon, or whatever really works for you. And what I found during this process is secretaries are much more responsive than professors, it turns out. I emailed the professor I worked for, no response, 2 or 3 emails. Finally emailed the secretary. Within 2 weeks later, I got contacted by a grad student. So that seemed to work for me. And the next part is really crafting the email or your communication. So you want to carefully craft your subject line so the whole email actually gets read. Professors are busy, and so you want to throw some zazz in there. Also, in the email, I can't stress this enough, please tell them it's free. Because if you don't tell them it's free, they think that you're asking to work for them and that they're going to have to pay for it. I even stressed this 3 or 4 times in my email, and that was the first question I was asked when I finally got in communication with the professor. So, for the love of God, put that in there. And lastly, really tell them what you're going to do for them. If you just say, oh, that's really interesting, cool, I want to work for you, but they don't think you're bringing anything to the table, they're probably not going to be as responsive as saying, I'm really good at signal processing and love working on these systems, and I believe that this is what this system needs in order to go to the next level. And I actually try to make a connection that way is much more powerful than just saying you want to work for. And then, this is the real finally, persistence and perseverance are a must. I went through 4 or 5 groups until I actually found one that agreed to host me. So you got to keep trying. So what you need, so first you need an invitation and permission from your advisor. After you've gotten those things, you need to write a 1-page summary and a budget, and you grab and send those to Ariel, and at which point Raphael and contact the professors get together in their hoods and decide who is to go. But I think so far it's been 100% success rate, so I wouldn't worry about it too much. So. And I'm going to end on acknowledgements and open up for questions.
Questions?
So, in one of the slides you showed that because of excess of oxygen you have feature shrinkage.
It's not really an excess of oxygen. It's just in sparse structures. So for example, that wave gutter ray, its periodicity was 80 microns. And so it was this 10 micron area that I was exposing, really surrounded by a sea of oxygen. So that would continually diffuse in and shut down polymerization at the edges.
So if you have dense structures, then you're going to have lower split as well? So that because of lack of oxygen, you're going to have bigger features?
You don't. So you can get bigger features, but not because of lack of oxygen. You get the reason sometimes you get bigger features is because of bimolecular termination and not linear dynamics of the photopolymer, not necessarily lack of oxygen.
So if you have a denser structure, your oxygen would be
So-
sufficient?
Yeah, so if you have a dense structure like I showed, you don't have as much oxygen to come in and shut polymerization down. You'll get diffusion of oxygen from the dark regions, but eventually it runs out, and you will get a carbon copy of your pattern.
Just curious, how many layers have you done, or how great a total thickness have you been able to pattern so far?
So we've done up to 5 millimeters thick, but generally we've been doing around 1 or 2 millimeters for our parts, with around 140 layers is the most I've done.
Have you measured how consistent it is, or?
Short answer is no. So it's really hard to measure deep index changes in materials. So the tools we have in our lab are is that QIS scanning that I showed, and that just measures the end facet. And the other tool is OFDR, and again, that just measures an end facet of, or the interface. We actually just got a microscope that we bought from InPhase, if you remember that company, that has the opportunity to measure three-dimensional deep index patterns. And so we hope to do those experiments later. Because it's a good question. We would like to know.
You use UV to produce your patterns.
Mhm.
Do you get smaller features if you use 2 photons on the wavelength, or even at UV?
Use 2-photon.
To generate your patterns. If you write your patterns with some light at 2 photons, that will allow you smaller.
Oh, I see. I'm sure we would, but then that would sort of, so the reason that we think that this technique is special is we actually can build structures relatively fast. And as soon as we go to 2-photon, everything slows down again. And so we probably would get better resolution, but it would sort of ruin.
I heard you should answer his question with the question, which 2 photons? What color? What's the 2-photon source?
Well, it will depend on the material that you use.
Now, depends on the laser you buy.
The laser? Well, I don't know, 2 UV photons.
You can't buy a pulse laser with 2 UV photons. There's a tense enough. So you're pretty much stuck with going 800 nanometers for TISAF to get enough photon flux to get a reasonable sensitivity to 2-photon regime. And so the answer there is no, you lose resolution, because you're getting the square of the profile, which you went from 365 to 800 nanometers in your diffraction limit. So most 2-photon results actually have worse resolution than 1-photon results, despite what they'll say in their abstracts.
Yeah, and so the 8 nanometers that I quoted was something where they really tuned in that 2-photon initiator, and they got that once. So generally they get around 150 nanometer resolution, which you can do better with 1-photon. I like.